Hello everyone, today let's take a look at quantipus number 38. In this question, we just need to write out the full binomial expansion of x plus y to the 7th. So we're trying to write all the terms in the expansion of this. We know that from the previous video, when we have 7x plus y's, we're going to have 8 different terms. So these are what our 8 terms are going to look like. I've omitted the coefficients because we still need to calculate those. But essentially, we're going to have our x to the 7th term if we choose an x from each one of these, and then we're going to have our x to the 6th and y to the 1 if we choose 6 x's from here and 1 y, and etc. all the way up to the point where we choose all 7 as y's. So for instance, say I chose an x from the first 6, so I'd have x, 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 and then maybe a y from the last one, then I'd have this. Well, obviously, this is just going to be the same as, let's say I chose 4 x's from the first 4, and then I chose a y for the 5th one, and then I chose 2 more x's. Well, then I'd have this, but these are exactly the same, right? They're both x to the 6th y. So when we end up summing all these terms up, we just need the coefficient here. We need the number of ways that we can arrange 6 x's and 1 y, essentially. And how many ways can we do that? Well, we've just been doing multinomials. We know exactly how to do this, right? We have 7 factorial terms. We need to divide by the number of like terms. We have 6 factorial ways to permute the x's and 1 factorial ways to permute the y's. This is just going to be 7. So our coefficient for this term is going to be 7 here. Now also note the symmetry down here. If we have y to the 6th and x to the 1, well, that's just going to be the number of ways to arrange 6 y's and 1 x, which is going to be exactly the same as this. So this coefficient is also going to be 7. For x to the 7th, we have exactly one way of arranging 7 x's. And we also have one way of arranging 7 y's. Now what about 5 x's and 2 y's? Well, let's just think about it. If I have 5 x's and 2 y's here, this is obviously another multinomial. We've done this so many times. We have 7 ways to permute these, and then we have to divide by the number of like objects as a factorial. So 5 factorial, 2 factorial. Now this is also just equivalent to 7 choose 5. We're just saying let's choose 5 of our places to be x's, or it's also equivalent to 7 choose 2. Let's choose 2 of our places to be y's and put the remainder as x's. So this is equal to 21. We know this. This will also be equal to 21 by the symmetry. So now let's do 4 x's and 3 y's. Well, it's just going to be 7, and we're choosing 4 of them to be x's. Or equivalently, we're choosing 3 of them to be y's. These are the same thing, obviously. This is going to end up equaling 35, so we're going to have 35 for both here and here. And this right here, this entire expansion, is going to be the final answer to our problem. So one more thing, let's just kind of generalize what we did here to the case when we have x plus y to the n. This is going to give us the binomial theorem and a more intuitive way to think about it. So what exactly are we doing? Well, we're taking some type of sum where we have some x and some y. So the x and y can be raised to powers such that they sum to n. So anything between 0 and n, right? So we can have k. Let's have k be our iterator. It can start at 0, raise x to the k, and y to the n minus k. And k is going to go from 0 to n. These are going to encode all of these terms like we had here when n was 7, all of these. Now let's account for these coefficients. So let me make some space here. Basically, we were using the multinomial. We were saying we have n factorial total ways of permuting these as if they were distinct, but they're not distinct. So we have to divide by the numbers up here, right? We have to divide by k factorial and n minus k factorial. And what do you know? This is just the formula for n choose k, so we could write it more simply as this right here, and this is going to be the binomial theorem. Obviously, thinking about it the first way is a lot more intuitive than this big clunky formula, but once we get it, we can derive a lot of cool properties. For instance, we're going to use this to prove inclusion-exclusion, and we're going to use inclusion-exclusion a lot in the coming problems.